Let's start again. I put up the camera now so you can see if I shift to the right. I'm in the middle now, so I should take this one. So I shift to the right, but it's only it's only so that you can see that I do it correctly. This lecture is not streamed. I cannot do that, but I record it and I put it on the homepage. So after each lecture, I upload a link to the video, which is on YouTube, and you can see it. So I have done so for a couple of weeks now, and I haven't heard anything about that, but it's there. So let's continue. I only have 2 examples left to show you. You have an example from R4. And I just, no, got the wrong paper, sorry. It's not from R4. It's much simpler. It's the example is simply this symmetric matrix. You have 3, 1, 1, 3. And it's obviously symmetric. And you want to calculate the eigenvalues for this matrix. And you take the determinant of 3 minus lambda, 1, 1, 3 minus lambda. And then you have the the characteristic polynomial. So it will be 3 minus lambda squared, and then minus 1. I won't do anything more about that because I'll just put this equal to 0. If I put this equal to 0, I get 3 minus lambda squared is equal to 1. And if this number squared here is equal to 1, then it's either 1 or minus 1. So I have that 3 minus lambda is equal to plus minus 1. And this means that I get lambda equal to 2 or 4. But you could compute this characteristic polynomial. You can find the discriminant and then compute the roots in the normal way. So what I'm going to do now is that I'm going to find the eigenspace corresponding to the eigenvalue 2. And when I put this 2 into my characteristic matrix and I augment it with zeros, I get this augmented matrix. 3 minus 2 is 1. You have a 1 here, and then 0 from the right-hand side, you get 1, and 3 minus 2, that is 1, and then 0 from the right-hand side. And obviously, you can subtract the first row from the second row, so you get the reduced matrix, which is 1, 1, 0, 0, 0, 0. and you can read off the solution, that is that E2 is the span of the vector. You could say if you take this as the second coordinate here as the free variable, then the first coordinate will be minus the second one. So you have an eigenvector like this. So this is E2. Now find E4, the second eigenvalue. If I put in 4 in this characteristic matrix here, I get, and then augment it, then I get minus 1, 1, 0, and here I get 1 and minus 1, 0 as the augmented matrix, and this will give the reduced matrix as, so I can swap it and I can add the two together, so I get 1 minus 1, 0, and then I get 0, 0, 0. And if I look at the solution to that system, I can find that E4 is the span of this vector here, that is 1, 1. This will satisfy this. So now you have two linearly independent vectors. You have minus 1 and 1, and you have 1, 1, and they are orthogonal, as they should be. I could write it minus 1 times 1, 1 is equal to 0. Now, it is orthogonal, but it's not normed. I have to norm these two vectors in order to get my orthonormal or orthogonal matrix Q. So if I take the vector minus 1, 1, and then I norm it, that is, I have to divide by the length of the vector, and the length of the vector is square root of 2. I get minus 1 divided by square root of 2, and then 1 divided by square root of 2. The other vector is 1, 1, this one, and I norm it again like this. So this is an orthonormal basis. The vectors, two vectors, are orthogonal, and the length is each 1. Let me try to illustrate this. If I take this vector here, it will be a vector of unit length like this. I could call it Q1. This vector here should be like this. This Q2. And then I can, let me draw the unit circle like this. And then you have the standard basis No, you call it, yeah, I and j. These are these two vectors. So there is a problem with this orthonormal basis, because when you look at the standard basis vectors, then they are, the orientation is from I to j in the counterclockwise direction, but for the q's it's the opposite, it's in the clockwise direction. And this is in fact, if you compute the determinant of q, then you get minus 1/2 and then plus minus 1/2. And this is minus 1. So this vector here is negative orthogonal. And if you don't like that, if you want the vectors to have the same orientation, then you could get that if you, instead of q1, takes the negative of q1. So let me call that q1 prime. And if you then compose your orthonormal matrix, orthogonal matrix from these two vectors here, you get, let me call this q2. Then the negative vector here, you have to change sign on the first column. You get, and the second column is unchanged. And here you see that the determinant of q2 is equal to 1. So this is called a positive orthogonal matrix. Last example. You have the matrix A here, 3, minus 2, 4, minus 2, 6, 2, and then 4, 2, 3. So you have computed that this has two eigenvalues, lambda 1 equal to minus 2 and lambda 2 equal to 7. And the eigenspace corresponding to minus 2 is the span of this vector, minus 2, minus 1, and 2. And the eigenspace corresponding to the eigenvalue 7 is minus 1 to 0 and 1, 0, 1. You see here, this vector here is orthogonal to this eigenspace here. If you multiply it out, you get plus 2, minus 2, 0. Okay? And in that one, you get minus 2, plus 2. So it's orthogonal. But these two vectors are not orthogonal. you have -1, +0, and then +0, that is -1, different from 0. So let me just write down. You have the three vectors, -2, -1, -2. And then you have -1 to 0. And you have u3 equal to. And this is orthogonal to these two, but these two are not orthogonal. So what can I do about that? I can do something smart. Because you know that this vector here, or u1, is orthogonal to both u2 and u3. And that is, it's orthogonal to the subspace that is spanned. It's orthogonal to all of this eigenspace here. So let me try to draw it. And this is only a schematic drawing. So I have here in this plane, I have drawn u, or I take a unit vector, and then I just calculate my first vector here. That is, I norm this vector here. And this vector here will be, it will be, the length of that vector is 4 plus 1 plus 4, that is 9, square root of that is 3. So this is -2/3. And then I think the last one here should be a +2. It's a +2 here. So that'll -2/3, -1/3, and then 2/3. This is my first vector. And now I should choose one that is perpendicular to that. You see, I draw here. My first vector, v1, that is perpendicular to all of this, which is the eigenspace corresponding to the eigenvalue 7. And now I choose the second one as this vector here normed. I know that these two vectors are orthogonal, so I can just divide by the norm here, which is 1 plus 4, that is 5. And then I get -1 divided by square root of 5, 2 divided by square root of 5, and 0. Now I have two vectors, but I miss the third one. And I can, of course, use the Gram-Schmidt method. But I can also use the fact that I know that the third vector will be in the eigenspace E7. And it will be and then of course it is perpendicular to V1, but it should also be perpendicular or orthogonal to V2. So I can just use the cross product of the two. Yeah. So I take as the third vector this cross product, and you see if I'm standing at the top of this one, let's see, it's this vector here. This is in E7, and all these angles here are right angled. And if I am at the top of this, then the direction of orientation is from V1 to V2. So if I do this, I'm certain that the orthogonal matrix will be positive orthogonal. So just calculate this one. And then this is minus 2/3, minus 1/3, 2/3, cross minus 1/5, and then 2 square root 5 and 0. And you get, the first one you get this, minus oh no, you get, yeah. So you have to take this, I just write the result. And then finally, minus square root of 5 divided by 3. So this should be, yeah. Okay, this concludes my lecture. So have fun with the exercises this afternoon. Okay, thank you.